everyone. You're watching the second part of the 29th video in the series Mathematical Methods for Economics. In the first part of the video, we covered linear approximations. The topic for this particular video is polynomial approximations. So, just to give a little bit of a background, let me quickly run you through the main message that we had for linear approximations, and then we'll use that to motivate the discussion further for higher order approximations. So, in the first part of the video, we looked at the linear approximation to a function as the tangent line to the function at the point x equal to a. So, the function is being approximated by the tangent to the graph of f, and that then gives us mathematically this result that f of x is approximately equal to f of a plus f prime at a times x minus a for x close to a. Now, there are two important things here. One we said was that this polynomial approximation that we are taking, which is f of a plus f prime at a times x minus a, this is linear in x, it is a linear approximation after all. And this resembles the function f of x near x of x equal to a in two respects. One is that the value of the polynomial at a is equal to the value of the function at a. You can see here that the value of the polynomial at a would be f of a, because here when you put x equal to a, the second term will vanish. And we know that p prime of x is equal to f prime at a. So, p prime at a will also be equal to f prime at a, and pictorially you can see that both the function and the polynomial approximation, which is this linear approximation, the tangent, both the function and the tangent to the function, they coincide not only in terms of their values, the value, but also both have the same slopes, right? And what we are trying to say here is, this is to motivate the discussion for higher order approximations, because if we want to talk about higher order approximations, we would want the polynomial to mimic the function even more closely. And in that sense, we would want the function to coincide, the polynomial to coincide with the function, not only in terms of the value of the function, the value of the polynomial and the value of the function, but also in terms of the first order derivative, the second order derivative, and high order derivatives, depending on the order of the approximation that you are taking. The question here is, why might we be interested in higher order approximations? So, to illustrate, let me give you a very simple example through this graph. Our graph here for the original function is represented by this curve in blue, and our linear approximation, which is the polynomial of the first degree, is represented by p1 of x. So, this is a straight line tangent to the graph of the function. And we are taking here, we are taking the approximation here at x equal to 1. So, the point here is that if the function has a sufficient bend, which it does in this case, if you look at the graph in blue, it has a sufficient bend. So, here we may argue that the accuracy of the approximation will tend to become worse as we move away from a, which is in this case 1. So, as we move farther and farther from a, with this function having a sufficient bend, our accuracy is going to get worse. So, in this sense, it might be useful to have a higher order approximation. In this case, for example, I have taken a quadratic approximation, which you can see is doing a pretty good job, a better job than the first order linear approximation around the point x equal to 1. So, this is what we are trying to say in order to motivate the idea of a higher order approximation, that our error, if the error is less, then it might work well to go with a higher order approximation. And this also kind of intuitively helps us answer the question whether we, what would be the order of the approximation that we would want to go up to. So, should we go for a second order or a third order? And here things would depend on the error term, or also on the kind of analysis that you are doing, because sometimes you just might want to just stick to a linear function, because linear functions are easy to manipulate. Now, let us specifically talk about quadratic approximations first before we move on to higher order approximations. Just as we assumed that the function is differentiable once to get our linear approximation, for quadratic approximations, we will assume that the function is twice differentiable and that the function is approximated by this polynomial of second degree, which is of the form capital A plus capital B times x minus a plus capital C times x minus a the whole squared. So, we are doing a little bit of cheating here. We are taking the polynomial already in the form where we have these terms x minus a, because that is the kind of end result we want, because we are taking the approximation around a. X, as usual, is close to a by assumption, and what we have here, if you notice, is that if we take the polynomial to be of this form that we have on the right hand side, then there are three coefficients that are to be determined. We have capital A, capital B and capital C. Now, because there are three coefficients to be determined, then mathematically we are free to impose three restrictions on this polynomial. And the restrictions that we'll impose would be that the function and the polynomial coincide in terms of the value. So, f of a is equal to p of a, f prime at a further is equal to p prime at a, and similarly the second order derivative is also equal to the second order derivative for p. The second order derivative of the function at a is equal to the second order derivative of p at a. So, with these three assumptions, we will go ahead to find the expressions for our coefficients a, b and c. Now, if you notice here, p of a, if I calculate p of a, I am going to put x equal to a. So, the second and the third terms will disappear, and that will give me capital A. And because by assumption p of a is equal to f of a, so we get the result that capital A is nothing but f of a. Further, if I calculate the derivative of p with respect to x, I have b plus twice c times x minus a, right? And this in turn implies that p prime at a is equal to capital B. Now, because p prime at a is equal to f prime at a by assumption, therefore, we have that f prime at a is equal to p prime at a is equal to b. So, our b is equal to f prime at a. Ultimately, we are going to be expressing these coefficients in terms of calculations that we get from the original function. Similarly, the second derivative of the polynomial with respect to x is 2 times c, right? If I differentiate this again, I get 2 times c, which is also to say that p double prime at a is 2c, and because by assumption p double prime at a is equal to f double prime at a, I have 2c equal to f double prime at a, and this in turn implies that c in terms of the original function is equal to half times f double prime at a. This in turn gives us the quadratic approximation to the function about x equal to a, which is f of x approximated by f of a plus f prime at a x minus a plus half f double prime at a x minus a the whole squared for x close to a. You can see here for yourself, we had got capital A as f of a, capital B as f prime at a, and capital C as f double prime at a divided by 2. So, I have just substituted for a, b and c here in our polynomial, and this is then the second order Taylor polynomial approximation to the function about x equal to a. Let us look at an example to illustrate a quadratic approximation, and we will work with the function that we had used for the first part of the lecture in order to get at the linear approximation, and the function here is the cube root of x, or x to the power 1/3, and the approximation here is about a equal to 1. So, because it is a quadratic approximation, you are being asked to go for. So, here the function would be approximated by f of a, which is f of 1, plus f prime at 1 times x minus a plus half times f double prime at 1 times x minus 1 the whole squared. All I have done is I have substituted a equal to 1 in the formula for the quadratic approximation. Now, we had already calculated that f of 1 is 1 because f of x is cube root of x. So, I have f of 1 is 1. F prime of x is 1/3 times x to the power minus 2/3. So, this then implies that f prime at 1 would be 1/3. F double prime of x is minus 2/9 times x to the power minus 5/3, and this then gives us f double prime at 1 equal to minus 2/9. But remember, because here in the third term you also have a 1/2. So, that is why when I multiply minus 2/9 by 1/2, I am going to get a minus 1/9 in the third term, and therefore, I have the function being approximated by 1 plus 1/3 times x minus 1 minus 1/9 times x minus 1 the whole squared. Now, let us just if you're just interested in seeing how you've done in terms of the approximations, if we compare things with what we had for the linear approximation, let us see how things are with the help of this picture. So, the graph here, the original function is given by the curve in blue, right? The linear approximation is as p1 of x, and our quadratic approximation, what we just got. So, I just plugged in these formulas in Mathematica, which is a software I use to get my graphs, and you can see here that the quadratic approximation is doing a much better job on both sides, though on one side it is, if I am reading things correctly, it is on the orange curve, the yellow curve is on one side of the blue curve, and it's on the other side, it's crossing this curve, but nevertheless, visually you can see that it's doing a better job of the approximation than the linear function p1 of x. And how well or to what extent it's doing a better job, if it is, that is something we'll get at in the next lecture, which would be talking in detail about the remainder or the error term. Now, what we can do here is that let us get a sense of that estimate that we were working on in the previous video, with the first part of this video, which was cube root of 1.03. Now, with the quadratic approximation, the cube root of 1.03 boils down to this expression, where you're again taking the approximation around 1, but x now is 1.03. Now, our quadratic approximation was 1 plus 1/3 times x minus 1 minus 1/9 x minus 1 the whole squared. So, here you have 1 plus 1/3 0.03, because 1.03 minus 1 is 0.03 minus 1/9 0.03 squared, and this then gives you 1.0099, which is actually what we got with the calculator also, up to 4 decimal places. So, we are getting exactly the correct answer up to 4 decimal places, which is really great. Let us look at another situation here that emerges. Here I have actually taken a polynomial function, which is 5 minus x squared, and for x close to 2, the question asks you to find the linear and quadratic approximations. Now, you can see here that the linear approximation will be given by f of 2 plus f prime at 2 times x minus 2. F of 2 here is 1, and f prime at 2 is minus 4. So, you get f of x is approximately equal to 1 minus 4 times x minus 2. This is a linear approximation. And if we go on further to find the quadratic approximation to this polynomial, there is something interesting that happens, and this is one result that you must keep in mind, because once I take the quadratic approximation, I have this third term here, which is 1/2 times f double prime at 2 times x minus 2 the whole squared. Now, f of 2 is 1 as we had calculated, f prime at 2 is minus 4 from the linear approximation. Now, f double prime of x is minus 2, which is also f double prime at 2. So, our f of x is going to be approximately given by 1 minus 4 times x minus 2 plus half times minus 2, which is minus 1, times x minus 2 the whole squared, right. This then gives us 1 minus 4x plus 8 minus x squared minus 4 plus 4x, which you can see here, the 4x will cancel out the 4x towards the end of this expression, and you get back exactly the same polynomial that you had started with. So, this actually gives us a very important lesson, which is that if you approximate a polynomial of the nth degree by the nth order approximation, then you are going to end up with the same polynomial, and you are the original function, that is, and the error is going to be 0. However, if you approximate a polynomial of the nth degree with a Taylor's polynomial of a lower degree, then some error will be involved. This is a message that this question is trying to get at. Now, in the last segment of this video, we will talk about higher order approximations, and we'll get at the general formula for an approximation of the nth order. And the objective here is to approximate the function over an interval centered at x equal to a with an nth degree polynomial. Again, we'll go through the same kind of exercise that we did for quadratic approximations. So here f of x is approximated by p of x. It's just that the exercise is going to be a little longer here because it's an nth degree polynomial. And this polynomial is of the form a naught plus a1 times x minus a plus a2 times x minus a the whole square, and so on till an times x minus a to the power n. Again, because there are n plus 1 coefficients to be determined, we will allow ourselves to impose n plus 1 restrictions on the polynomial, and these restrictions are just meant to make the analysis really tight and make the polynomial mimic the function as closely as possible. So the value of the function is the same as a value of the polynomial at a, the first order derivative of the function, the second order derivative, and up to the nth order derivative. All of these derivatives are equal to the corresponding order derivatives for the polynomial p. Let's see how this pans out. So if we look at f of a by assumption, that is equal to p of a, and f of a is nothing but a naught, excuse me, p of a is nothing but a naught. So a naught is f of a, that is the first result we have. We can substitute a naught by f of a. Now p prime of x is a1 plus twice a2 x minus a plus thrice a3 x minus a the whole squared, and so on till n times an times x minus a to the power n minus 1. Now, what I would like you to start doing now is look for a pattern in these derivatives, because this helps us generalize to the nth order derivative. Now, if you notice here, if I look at p prime of x, that's a1 plus 2a2. So we are basically taking these coefficients and keeping them as they are, and the last term is basically if I am taking the first order derivative, then the last term we will be subtracting a 1, right? Now if I look at the second, let me just back up. So p prime at a would be equal to a1, and because that is equal to f prime at a by assumption, so we get the value of a1 also, which is f prime at a. Now p double prime of x will be 2 times 1, which is 2 factorial, times a2 plus 3 times 2, so we go down one step. So if it's a second order derivative, we go down one number for each term. So 3 times 2 times a3 times x minus a, right? So the power in the previous derivative was 2, so now it's going to be 1. We go down 1, and till the last term, which is n times n minus 1, go down one number, times an times x minus a to the power n minus 2. Because it's a second order derivative, here we have n minus 2. Similarly, let's just do 1 or 2 more exercises of this kind, because that will help us get the drift. So p double prime of x was this expression, which implies that p double prime at a is 2 factorial times a2, because all the rest of the terms will disappear. And because this is equal to f double prime at a by assumption, we have that a2 is equal to 1 by 2 factorial f double prime at a. Now similarly, the third derivative of p is 3 times 2 times 1 times a3. The first term is always the subscript of capital A will always be the same as the derivative. So, and you're going down two numbers, which is one less than the order of the derivative, and you go down to the last term, which is n times n minus 1 times n minus 2 times an times x minus 1 to the power n minus 3. Okay. So this then gives us the third derivative at a, which is 3 factorial a3, which is by assumption equal to the third derivative of the function. So a3 in turn is equal to 1 by 3 factorial, the third derivative of the function at a. And I hope you're now getting the drift. You can actually do this with pen and paper, and you'll start seeing the pattern yourself. It's easier to do it when you do it yourself. And finally, you can similarly calculate the fourth order derivative, and you get a4 as 1 by 4 factorial, the fourth order derivative at a. And finally, you have the nth order derivative, which is going to be n times n minus 1 times n minus 2 go all the way down to 1, and times an times x minus a to the power n minus n, which is 0. So, this term x minus a will vanish, and this then gives us the nth derivative of the polynomial at a as n factorial times a n, which is equal to, by assumption, to the nth derivative of the function at a. This then implies that a n is equal to 1 by n factorial, the nth derivative of the function at a. Okay, let's collect all these results now. So, we've got some interesting patterns, and a0 was f of a1 was f prime at a2 was f double prime at, a2 was 1 by 2 factorial f double prime at a, and so on till an, which is an times x minus a to the power n. So, 1 by n factorial, the nth derivative of the function at a times x minus a to the power n, that is the last term. So, this is then the nth order Taylor polynomial approximation of the function around x equal to a, and this is the general formula. We first, in the first part of the video, we looked at the linear approximation, which would just go up till n equal to 1. So, that is just going to be these first two terms here. And similarly, if I wanted the quadratic approximation, it would be these first three terms, just exactly what we had derived. So, it is a beautiful pattern, and you can go up till the nth term in the same way. The pattern is just very easy to remember. It's a very simple formula, and as I said earlier, that this is the nth order Taylor polynomial approximation, and if I take this approximation around a equal to 0, which is a special case around x equal to 0, that is called the Maclaurin polynomial approximation, because this name is used in practically every textbook that you cover for approximations, polynomial approximations to a function. So, this is something we must take note of. Okay, let's just go through one or two examples before we end this discussion. This question asks you to find the third order Taylor approximation of the function 1 upon 1 plus x for x close to 0. Here it is a third order Taylor approximation, so n is equal to 3, and because you have to take the approximation around x equal to 0, so a is equal to 0, and the approximation that we are going to use, a polynomial we are going to use is of the third degree, so that is f of 0 plus f prime at 0 times x, and this is actually a Maclaurin's expansion because a is 0, plus 1 by 2 factorial f double prime at 0 times x squared, plus 1 by 3 factorial f the third derivative at 0 of the function times x cubed. Now, f of 0 you can see from the function, the original function, it is 1. F prime of x is, because I can write the function as 1 plus x to the power minus 1, that can be, so f that gives us f prime of x is minus 1 plus x to the power minus 2. F double prime of x is 2 times 1 plus x to the power minus 3. The third derivative is minus 6, 1 plus x to the power minus 4, and once we take these derivatives at 0, we get f prime at 0 as minus 1, f double prime at 0 as 2, and f the third derivative of the function at 0, which is minus 6. And once we plug these values in, we get f of x as approximately equal to, and before I forget, this is very important, this is not an exact value, this is an approximation, so always remember to use the approximation sign. So, f of x is approximately equal to 1 minus x plus x squared, because once you divide 2 by 2, you are going to get a 1 minus x cubed. That is our third order Taylor approximation for the function 1 upon 1 plus x for x close to 0. Finally, let us take up an application from economics just to see how people use this kind of an approximation or approximations, because we are ultimately doing mathematical methods for economics. So, here we have this example which says that in connection with the study of attitudes towards risk, the following approximation to a consumer's utility function is encountered. So, the utility function is given by u, And the function, without getting into the details of these terms, we have this approximation. We are here just going to be concerned about the way we get this approximation, which is exactly what the question asks you to explain. Explain how to derive this approximation. U of y plus m minus s is approximately equal to u of y plus u prime at y times m minus s plus half u double prime at y m minus s the whole squared. Now, you can clearly see here this is a Taylor's polynomial on the right hand side. It is a Taylor's polynomial approximation of order 2. So, n is equal to 2 here. Our function is this function u. Because the derivatives you can see are being taken at y, so we are basically taking the, we are evaluating the derivatives at y. So, a is equal to y, and because a is equal to y and this is our x, u of y plus m minus s, so y plus m minus s is x, right. So, you can see here that m minus s would then conform to our x minus a, because x minus y is nothing but our x minus a, which is m minus s. So, with these adjustments, you can make this conform to your Taylor's approximation, and this is how you will explain how this approximation is derived. This is all we have for quadratic and higher order approximations to a function. Thank you very much.